This final section, 13.5, is on viscous flow, and this is the fifth section of our chapter on fluids. There are two equations that are extremely important in the study of viscous flow, and the first one is really the equation that defines viscosity. And we do that, we define our viscosity as the force that's needed to keep a moving layer of this viscous fluid moving at a constant velocity. Well, how do we do that? We want to know the force. So we're going to describe a force that's given in this equation. And this force is going to be equal to a constant, which we call eta, times, and I'm going to draw a diagram over here. We want to imagine that we have an immovable plate here, and we have a fluid here, and another plate here, and we're going to take this plate. This might be water in here. These might be two steel plates, and we're going to take this plate and we're going to move it in this direction with a velocity v. And this plate is going to have an area A, and these plates are going to have a distance apart, y. Now, if you stop and think about it, the force that's going to be necessary will not be as great if I have a great separation here. So this is going to be inversely proportional, as you might guess, to the distance between, because if I go twice as far away, it'll be twice as easy to slide this, because if you think of the torsion or the twisting of this fluid, then if I have twice as much fluid here, it'll be twice as easy to move this plate forward, because I'm not having to twist it so dramatically, only half as much. If you could imagine the fluid being twisted to a new position, if it's twice as thick, it only has to do half as much. And also the area, if I have twice the area, then I would need twice the force. So it's going to be proportional to the area. If I want it to go twice as fast, then the amount of fluid that's got to recover from this or drag backwards is going to be proportional to the velocity. So our final equation is going to look like this. And this is our equation that defines viscous flow. The force needed in order to move a layer of viscous fluid, a layer that's attached to this plate here, that has area A, a velocity v, and has a distance y from another immovable plate, the one at the bottom, and the constant proportionality here is eta, and eta is equal to the coefficient of viscosity. So this eta, it looks like an N, it's a Greek letter, has kind of a long tail to it, and that's used for as a representative of viscosity. And if you go back and check, this will have units of pascals times seconds. Pascals times seconds. And a pascal times a second is a poise. So 1 pascal times 1 second is 1 poise. This is the unit of viscosity. That would mean if 1 Newton were needed to keep two plates that are 1 meter apart moving at a velocity of 1 meter per second when their cross-sectional areas are 1 square meter, that would be a viscosity of exactly 1 pascal second, or 1 poise. Because this is the way we can define our concept of viscosity, because viscosity doesn't like for the fluid to slip over itself or over another surface, and this is how it's defined. The other law that we want to discuss, Suville's law, gives the volume of the flow rate in a pipe. So we have a pipe here, and we say, okay, in this pipe we want to move some fluid. And this pipe is going to have a radius r, going to have a length L, and it's going to have a pressure P1 at this end and a pressure P2 at this end. Now, if it has a pressure the same at both ends, then in fact the fluid's not going to move in the pipe. And obviously, if it's going to be twice as long, it's going to be half, it's going to be a lot harder, and it's going to depend upon this radius. And it's very interesting to look at this rate, and this is the flow rate. Now, by flow rate, we really mean here a rate Q, which is the change in volume over the change in time. It's the flow rate. How much volume per unit time of this fluid? And the answer is, for a pipe, this is going to be pi times r to the fourth power, P2 minus P1, divided by 8 times the coefficient of viscosity times the length. Well, part of this you could have imagined. You could have guessed that it was dependent upon the distance, the difference in the pressure. Because if the pressure is twice as great, you're going to get twice the fluid flow. You could also say it's inversely proportional to L. So you could have guessed this part. Because if it's half as long, then you'll move twice the fluid. So if I replace L by half L, I'll get twice the volume per unit time. So these two units, these two components, you could guess. You might also guess that it's going to be inversely proportional to the viscosity. Because if the viscosity is twice as great, then only half as much fluid would flow, and so then it should be inversely proportional to the viscosity. What might be hard to imagine is how this arises, and we will not derive that, we take it as given. It's a good experiment, a good experimental result. So this law is useful for looking at how much we can move fluid through a pipe. That certainly applies to pumping water through pipes or pumping oil through pipes for pipelines or other fluids. However, we need to remember here that we're talking about regular fluids and nothing with turbulent flow or things of that nature.